Hello everyone, welcome to lecture 33. So here we are actually going to continue upon our previous discussion from the previous class, that is which is on thermodynamics and how equilibrium properties can be looked at as arising out of thermodynamics, right. So we have defined what thermodynamic potentials are. So go back to the analogy of spring mass. In spring mass you always have a potential, an underlying potential, and if I need to know what is the spring constant, I need to look at the curvature of this potential, right. So with respect to the strain, with respect to the extension of the spring, right. So similarly, so all equilibrium properties, and that K right, is an equilibrium property, which means that if you deviate, if you displace the spring slightly away from the equilibrium, it would want to come back to equilibrium, right. So it is it tells you what is the restoring force to bring back the system to equilibrium, right. So with that in mind, any property, so an equilibrium property has an underlying potential, and we try to define a set of these potentials, and from those potentials we are looking at their curvatures, and we are trying to see that these curvatures are nothing but the properties of interest, right. So for example, here in the last class we have defined a few of these potentials, right. So if I go here, you can see there is a phi 1 which is u minus Ed, there is a phi 2 that I defined which is u minus Ts minus xx minus Ed. Now phi 2 is a potential that I will be using if my control variables are entropy, if my control variables are charge, and if my control variables are strain, right. The other way around. So this one. So if my control variables are temperature, stress, and electric field. Now so I can also define phi 3 as follows, and phi 3 is so my control variables, if I start using phi 3, are so you have temperature, strain, not stress, and electric field, right, and so on and so forth. So based on this we can also look at, so last time we have looked at what dou phi 2 by dou E1 is, and then dou 2 phi 2 by dou EI square, and that is nothing but my dielectric constant, right, or negative of dielectric constant, that is the curvature of this potential phi as a function of E. E is the cause and the displacement is the effect, right. So the thermodynamic potential, we drew an analogy between the thermodynamic potential and the spring constants, right. Both of them actually store energy, and this energy is thermodynamic energy, right. So this is energy that is stored and not dissipated, okay. Then we went ahead and then we said, all right, so actually these are tensors, the epsilon ij is a tensor. So we have this property for all these thermodynamic potentials because they are what are called analytic functions, right, and analytic functions have this property that whether you differentiate with respect to x first or y first, it does not matter, both of them should be equal, and based on that we have differentiated my phi 2, which is the thermodynamic potential, with respect to Ei first and Ej next, and we have obtained epsilon ij or minus of epsilon ij. And we say that even if I exchange the Ei's and Ej's, so that is I differentiate with respect to Ej first and then Ei, and still I get minus epsilon ji, and just the fact that these functions are analytic means that these two should be equal, or epsilon ij should be equal to epsilon ji. This is not only so this is valid for any second rank tensor which is which is an equilibrium property, right. So all second rank tensors are symmetric in nature, so are symmetric in nature. Now that is true, that is this fact we have been using for a while, but in terms of equilibrium properties we have shown you the proof just now, right. Non-equilibrium properties such as conductivity, you have to wait for the next module to actually prove it. And last class we ended by saying, okay, why don't you actually take the stiffness tensor and prove that Cijkl is equal to Cklij, okay. So let us start there, then I again take my d phi 2, let me go back and see what phi 2 is, that is minus s dt. We will see what this s is the entropy dt minus small x dx minus di dEI, right. Okay, so now this is also xij, xij, right. So, which means this is a summation of all the ij indices, right. So, I can have other indices also, but it is a complete summation of this is the Einstein notation of writing the tensors, right. So, now if I take a dou phi 2 by dou x ij, right, keeping everything else constant, that is temperature, EI and all the x's which are not xij's, right. So, xkl where kl is not equal to ij, right. So, if I keep all these parameters to be constant, I get this to be minus xij, right. So, this is just strain, right. So, the first derivative of free energy with respect to stress is nothing but the strain, right. First derivative of free energy, as we have seen in the last class, with respect to electric field is nothing but the displacement, right. So, this is the free energy that I have defined in a way that I have stress as my cause, electric field as my cause and so on and so forth. This is the phi 2. Okay. All right. So, then let me then do something else, which is I know that dou phi 2 by dou xij is equal to minus xij. Then I again take a double differential of this, but this time instead of ij I am going to take it with respect to kl, and this will be xij, and that would be minus dou xij by dou xkl. And so, that is the change of strain with respect to stress, right. So, stress is going to be your cause, strain is going to be your effect, right. Strain is going to be your effect, and what relates the both of them is the compliance, right. So, dou x by dou x, that sort of a tensor gives you the compliance, right. Gives you the so the compliance is the s, right. So, I have to write it as s, small s. Okay. Okay. So, that will be minus s ijkl, right. Okay, but nothing prevents me from doing it the other way around, which is dou phi 2 by dou xkl is minus xkl, and if I again take a second derivative of it with respect to dou xij, so that would be dou by dou xij. Now, you know what are all constant, the temperature is constant, the electric field is constant, temperature is constant, electric field is constant, and that is equal to minus sklij, right. So, what have you ended up showing? You have ended up showing that Sijkl is exactly the same as sklij, because this one and this one are one and the same, right. So, these are analytical functions, which means that these are one and the same. Since phi 2 is analytical, right. So, let me call this 1 and let me call this 2. 1 and 2 are the same. Okay. So, as a result, in Voigt notation, right. So, these ones will condense as ij will have one index, kl will have another index. So, this will be lm, that should be equal to sml, right. So, my so I have already used this fact to say that the number of components, right, is ideally 6 by 6, right, but in the 6 by 6 tensor, I only have 21 independent elements, right. So, 6 by 6 ideally I should have 36 elements, but I get down to 21. You can look back at the notes of the compliance and the stiffness tensors that we did. Okay. Now, if I want to show the same thing for stiffness, right. So, Cijkl equal to Cklij, then I have to select another potential, but this time this potential phi should be dependent on, it's okay, temperature, electric field is fine, but it should be dependent on strain, not stress. Okay. So, and that is easy to define, right. So, I can go back to my u, and you know, so yeah, so for example u, where is u? Du, if I look at du, yeah, so du is already dependent on you know, strain. So I am just going to define something like u minus Ts minus Ed, right, and the strain part is just remaining as it is, right. So I am going to define my phi 3 or phi 4 as u minus Ts minus Ed, right, and that would be dependent on temperature, that would be dependent on electric field, that would be dependent on strain, because I do not have a minus xx, that does not exist, right. So if that exists, then the dependence will, then that is phi, that is the same as phi 2, and the dependence will go on to stress. Okay. So then if I do the same you know, mathematics, then I would be able to show thatCijkl equal to Cklij. Okay. So essentially, you know, the curvatures of phi or potentials, thermodynamic potentials, here I do not really look at the sign of the curvature. Okay. So are material properties, the sign tells you something about the stability, but you know, so let us not worry too much about that. That is number 1, and then you know, so you also show that you know, the symmetric nature of the tensor of you know, second rank, fourth rank tensors arise from the analytic nature of phi. Okay. That epsilon is a symmetric tensor is just a mathematical fact. Okay. So you know, so that, for example, epsilon ij is symmetric is a mathematical fact. Sorry, is a mathematical fact. Okay. All right. So let us look at what are the other you know. Okay. So phi 2 is, or d phi 2 equal to minus s dt, right. So phi 2 is one of the important potentials, minus e d I d e I minus dx, but then I have a small x. Okay. So this is one of my good important potentials. If I just look at dou phi 2 by dou t, I have a minus s, right. So keeping ei's and all the xij's constant, right. And if I take a double derivative of that, right, dou t square, that would be minus dou s by dou t, and minus dou s by dou t I know is a property which is Cp by t. Actually it is minus Cp by t. Okay. So this is because of the way I am defining dou phi and the convention that I use to define u, right. So u equal to q plus w, that is how I defined u, right. So because of this convention, you know, so it the minus sign comes here, the minus sign you know, directly arises from the convention that I used, okay, or du equal to dq plus dw, right. So this is the first law of thermodynamics. Some people use the convention to be du equal to dq minus dw, this is convention, another convention, right. So then you know, then I will not get these minuses if I use this convention. Okay. So but it does not matter, right. So for now, that is why I am not very much worried about what sign this has, whether it is minus or plus, it does not matter. That tells me the stability of the property, right. But you know, so dou 2 phi by dou t square actually tells me, the curvature actually tells me that there is a property, underlying property, which is Cp. Okay. If I go the other way round, that is I define another thermodynamic potential which is just Tds, right. So minus you know, or I am just going to define u, right. So Tds plus Edd plus you know, so I am just ignoring the indices, there should be of course indices x dx, right. So this is u, right. So this is, I come back to my first thermodynamic potential which is u, I do dou u by dou s, right. So that is nothing but temperature, right. So dou u by dou s is nothing but the temperature, and dou 2 u by dou s square by dou s2 will be dou t by dou s, and dou t by dou s is again so t by Cp, right. So, this is my converse property. If you look at the triangle again, if we go back to a few classes, couple of classes ago, and look at my sorry, I have to go back. Yeah, here in this triangle, right. So, there is a Cp by T and there is a T by Cp, right. So, both of them arise as some sort of a thermodynamic property. Okay. So, which potential do you consider is the thing? Okay, all right. So, so similarly, so if I just look at dou u by dou 2 u by dou d square, that would give me something called beta, and beta is beta ij, and beta ij is the inverse tensor of epsilon ij. Okay. So, and so on and so forth. So, all the thermodynamic properties arise as curvatures, right, of these potentials, right. So, let us again rewrite that statement. All equilibrium properties are curvatures of potentials respective thermodynamic potentials but that what do they physically mean? That they are mathematically curvatures of some potential is okay, but physically they represent the extent of restoring forces to bring back a system which is displaced from equilibrium back to equilibrium. Okay. So, so for example, phi 2 as a function of electric field can be a function like this, right. So, this is my equilibrium point, this is the equilibrium point. Okay. Okay, so let us make it more symmetric, right. So, if I displace phi 2 away from equilibrium, right, so let me point it out in some other color. If I displace phi 2 away from equilibrium, what is the force acting on phi 2 so that it can come back, it is going to come back, right. So, the restoring force back to the equilibrium point, right. So, that is determined by the epsilon ij, right. So, which is the dielectric constant of this material. Okay. All right. So, that is the direct properties. What about the coupled properties? Okay. So, let us go back to our favorite potential d phi 2. Now, d phi 2 is what is it, minus s dt. So, phi 2 is a potential that is dependent upon t capital X capital E, right. So, that is minus s dt minus dx will come minus de will come. So, but this is di dei, this is small x I j capital X I j, right. Okay. So, this is my d phi 2, right. So, now first let me do the following, right. So, I am going to take a derivative with respect to E I, right. So, what is dou phi 2 by dou E I, keeping the temperature, the stresses constant, is nothing but minus d I. Okay. So, this is the first thing. Then I am now going to take a derivative with respect to, this time I am going to dou E I, this quantity I am going to take a derivative with respect to dou x I j or x j k. Okay. So xij means that also has its summation, right, over ij. So, all the j, k, kl, everything will come in here. Okay. So, what is that? That is minus dou di by dou xjk, right. So, I am applying a stress xjk, x12 or x22 or whatever it is, in the stress tensor I am applying a stress and I am generating a polarization, right. So, what is this? This is nothing but my piezoelectric effect, piezoelectric property, and I am going to write it as dijk. Okay. So, this is this is just a piezo, or I am just going to transfer the minus here. So, this is piezoelectric effect. Okay. So, first I take the phi 2, I first take a derivative with respect to EI, keeping all the others constant, and then I take of the resultant quantity which is di, I take a derivative with respect to xjk, keeping now I keep the electric field constant or temperature constant and so on and so forth. Okay. So, then I get dijk, right. So, but this dijk you must understand is at a particular value of stress, particular value of electric field and particular value of temperature. Okay. So, because I am keeping these things constant here. Okay. All right, or depends on stress, electric field and temperature. So, you can change the stress in the material and change the piezoelectric coefficient. You can change the electric field in the material and change the piezoelectric coefficient and so on and so forth. Okay. Okay, and you can change the temperature of the material and change the piezoelectric coefficient, right. So, this is something that I am not going to carry over from now on, but you want to keep that in mind, that this is dependent on x, e and t, right. So, this dijk I am so I have calculated this dijk at a particular electric field and at a particular x because here I put the xij constant at a particular stress state, right. So, whichever is given here, that stress state is held constant and this electric field is held constant, right. So, this dijk so is calculated at a particular E and particular x. So, this will only be dependent on temperature in that sense, right. So, E and x are constant, right. So, temperature can change and dijk will change with temperature, but in general dijk will be a function of E, x and t. Okay. So, that is something to keep in mind. Now, so we have this, right. So, this is the phi 2 is again our good friend analytical function. So, now I am going to do I am going to change the order of differentiation. So, now first I am going to differentiate with respect to x jk, and then I am going to differentiate with respect to EI, okay, and then there is going to be a minus. Now, what is this quantity? So, again number 1 and number 2 are one and the same, 1 equal to 2, because phi is an analytic function. Okay. Now, if I do that, what is going to be the resultant so dou phi 2 by dou xj is so xjk, right. So, that is the strain comes into picture and differentiated with respect to electric field applied in the I direction. Okay. So, minus of this, right. Okay. So, here what am I doing? I am applying electric field and measuring the ensuing strain, right. So, I apply electric field EI and I get strain xjk. Here I am applying stress and measuring the displacement, measuring the charge. Okay. So, this is what is this? This is converse piezoelectric effect. However, if 1 equal to 2, this one since 1 equal to 2, this one should just be equal to dijk, right. Sorry, so there is no minus here. So, this one should just be equal to dijk, right, because 1 equal to 2, this quantity should be equal to this quantity, right. So, what you have shown is di by dxjk, right. So, this is how dijk is defined, which is my piezoelectric coefficient, is nothing but whether I apply stress in the so the jk tensor of stress and measure polarization along the I direction, or whether I apply electric field along the I direction, the direction of electric field is the same as direction of polarization, and measure an ensuing strain along the jk tensorial element of strain. These are one and the same. So, what I get is dijk, right. So, in you can also express it in terms of Voigt notation. So, it would be di some L, right. So, jk condenses into L. Okay. So, one may need to pay some attention here. If I am saying dil, right. So, that means that my either if I am doing a stress experiment, my stress is in the L, I am looking at the Lth Voigt component of stress, and I am looking at the ith component of d. So, okay. So, this is straightforward, this is okay, right. But that is also equivalent to I am looking at the the EI, I am applying EI, right. So, not EJ or EL or whatever it is, I am applying EI and I am measuring strain along the L component, right. So, the Lth component Voigt component of strain. Okay. So, these are one and the same. Okay. So, the IL notation one needs to keep in mind that if I am doing a stress by electric field, the stress has the L, whereas electric field takes the I. But if I am doing just a polarization by stress, let me rephrase that. If IL notation, if I do a strain by electric field, I apply electric field and I get strain, right. So, then I is for the electric field and L is for the strain, right. But if I am doing the opposite experiment, which is I am applying stress and measuring the displacement, then L goes for the stress and I is for the displacement, okay, or electric displacement or polarization. Okay. So, what this has shown is so what we have alluded to earlier, that is the piezoelectric effect and the converse piezoelectric effect. Okay, are one and the same. Okay, but you have to measure them at So, what are you fixing, right? So, dijk measured at a given temperature, measured at a given electric field and measured at a given stress, right, will be equal to the converse dijk, right. So, will be equal to the converse effect, okay, measured at the same parameters. So, that is what thermodynamics is telling us. Okay. So, just by virtue of so again that converse piezoelectric effect and direct piezoelectric effect are one and the same magnitude wise, right, is a direct consequence of your the thermodynamic potential being an analytic function. So, this is a mathematical fact, right. Now, when you are doing experiments, you can find that these are slightly different in nature, but so that will come because of some other experimental conditions like clamping, etc., right. So, you may be measuring dijk at slightly different stress state compared to the converse effect where the stress state will be something else, right. So, because of these differences you will measure slightly different values, but thermodynamically if I fix my stress, if I fix my electric field, if I fix my temperature and somehow do the measurement of both direct effect and the converse effect, both of them should be exactly the same. Okay. So, let us get a feel for this, right. So, what is dijk if I am doing, what are the units of dijk? Okay. So, if I do a direct measurement or direct piezoelectric effect measurement, so I am applying stress, right, and I am measuring charge, and stress is Newton per meter square, charge is Coulomb per meter square. So, what you get the unit of this is Coulomb per Newton. or typically this is expressed as picocoulomb per Newton, because most of the materials have values of dijk in this order, right. So, I have something like 6 picocoulomb per Newton, right. So, this is these are the values of a material called aluminum nitride, right. So, 6 picocoulomb per Newton. So, pico is 10 power minus 12, right. So, you generate 10 power minus 12 coulombs of charge by applying 1 Newton of force in some sense. Okay. Yeah. So, the values are typically of this is of D33 actually, that is the tensor of aluminum nitride, right. Let me write it here, D33. If I take another material called PZT, right. So, I said PZT is a very famous, this is lead, zirconium, X, titanium 1 minus X, right. So, oxygen. This is a perovskite material, this is my A side, this is my B side, this is my O side, right. So, we have looked at what perovskites are, and if I look at the piezoelectric coefficient of these sort of materials, they are typically hundreds of picocoulomb per Newton, right. Depends on the composition, depends on so this is just to get a feel for the numbers. Okay. Now, what about the converse effect? The converse effect is you apply an electric field and you measure the strain, ensuing strain, right. So, electric field has a unit of volt per meter, right, and the strain has no units. So, typically this is meter per volt, right, or the way we express it is in picometer per volt, right. Now, you can just take so the units need to match, right. So, by saying that the converse effect and the direct effect are the same, right. So, same in magnitude, I am going to tell you that picometer per volt is the same unit as picocoulomb per Newton, and you can go home and prove this, right. So, just see that the units or dimensions of direct piezoelectric coefficient, which is dou d by dou x, is the same as that of converse piezoelectric coefficient, which is dou x by dou E, but here it is I, here it is J. Okay. All right. So, in the remaining time, let us look at one more property, right. So, let us go back to our phi 2, again d phi 2 equal to minus s dt minus d dE minus small x capital dx, right. So, so all the intensive properties are here and all the extensive properties are here. So, that is why phi 2 is a good potential. It segregates the intensive and phi 2 segregates the intensive and extensive properties. Intensive properties as cause and extensive properties as effect. Okay. So, phi 2, that is why I keep on going back to phi 2, it is a good potential. Now, let us so earlier we have looked at, this is the electromechanical problem, right. Right. Now, let us look at the electrothermal problem, right. So, what about the electrothermal problem? Which means I have to consider these two terms, right. So, let me exactly do the same thing, dou phi 2 by dou E I, right, and then dou by dou T, right. That should be equal to minus dou by dou E I dou phi 2 by dou T. Okay. Now, what is this? This is actually dou phi 2 by dou E I is d I, So, minus dou di by dou t, right, and that should be equal to minus dou by dou ei, and dou phi 2 by dou t is nothing but the entropy. Okay. All right. So, what is this? Dou minus dou di by dou t, we have defined this to be the pyroelectric effect coefficient, right, or pi I. So, pi I, what is pi I? I change the temperature of the system and I generate polarization in the system, right. So, these are pyroelectric materials. We have discussed a bit about pyroelectric materials. Pyroelectric materials are used as sensors to sense fire in a fire alarm, for example, right. So, what are called bolometers are made out of pyroelectric materials and so on and so forth, right. So, they have good technological application. One of the pyroelectric material is what is called, one of the standard pyroelectric material is what is called lithium tantalate, right. So, this is one of the well known pyroelectric materials. It is available as single crystals that you can buy and then use in all these sensors, etc., right. Okay, so that is the pyroelectric coefficient. Now, what is this? Here I am applying electric field and generating heat, right. So, when I apply electric field I generate entropy, right, so typically what happens is, let us say my polarizations are all not very well ordered. So, the entropy of this system is large. Then I apply an electric field on this material and the entropy, so all these things start ordering with respect to each other. So, then the entropy becomes smaller, right. So, typically the value of dou s by dou E is a negative value, just like pyroelectricity is also a negative value. Dou I by dou t is negative. So, I add a minus and make the pyroelectric coefficient positive. Similarly, dou s by dou ei is also, by applying an electric field I try to order the materials more, right. So, this is this value typically is a negative value, that is why I put a minus and define this as what is called an electrocaloric effect, right. So, an electrocaloric property or an electrocaloric effect, right. So, by applying electric field I am either generating entropy or reducing entropy in the system, right, or in other words, so by applying an electric field putting in entropy or removing entropy is equivalent to putting in heat or removing heat. I am either heating or cooling a material, right. So, these are all what are called electrocaloric materials. And you can use them to make to run your refrigeration cycles and so on and so forth, right. Because once I put in an electric field I can cool the material, I can run it through a cycle, the so called what is called a Brayton cycle or a Carnot cycle, right, where the refrigerant is now my material, right. I am just mentioning this, I am not going to details of this, probably we will see if we can make an assignment problem out of this, and so I can refrigerate, right. So, I can cool down devices or materials. However, the more important thing is a material which is a good pyroelectric material is a good electrocaloric material, right, and that is the magic of thermodynamics, right. So, that is nothing but it is just the magic of thermodynamics. Which says that if I have if I am generating polarization by changing temperature, that is equal to generating entropy, entropy does not have coefficient, by changing the electric field, right. So, these are one and the same, and these are so this is a different experiment altogether, right. So, here I am applying temperature and measuring the charge, right. Whereas here I am applying electric field and measuring how much the material is heating or cooling, applying electric field and measuring the heat exchange, right. These are different measurements, but the magic of thermodynamics means that the properties are one and the same. Okay. So typically these measurements are hard to do, right. So how do I know how much heat am I putting into the material, right. So the electrocaloric effect measurements are not very straightforward. They are doable, of course. You have what are called electrocaloric efficiencies, so the cooling that you get because of the cooling or heating that you get because of having an electrocaloric material, you can directly measure temperature and try to understand what this effect is, right, using IR cameras, etc. But it is not a straightforward measurement, right. But polarization, change in polarization as a function of temperature is a straightforward measurement. Polarization, I just need to, as a function of temperature, is a straightforward measurement. I just need to cycle my device across certain temperature varies with time like this, right, and then so then I look at what the current is in my device, and the current will go like something like this, right, and from current I can actually calculate what is the polarization by integrating it, and polarization also will go something like this as a function of time, right. So polarization will increase, polarization will decrease, so up to here, and sorry, let me remove this axis, and polarization will again increase, right. So these are typically the measurements that I am doing, and so I have polarization versus temperature, which is either linear or which is some sort of hysteresis, which looks something like this, right. So looking at so I have polarization versus time, I apply temperature versus time, right. So looking at these two data sets, I can have polarization versus temperature, right, and I look at the slope of polarization versus temperature, dP by dt is nothing but my pyroelectric coefficient minus pi. Okay. So these are easy measurements. So I can qualify a material to be a good electrocaloric material or not just by looking at its pyroelectric effect, right. A material can be qualified to have a good refrigeration ability, or through electrocaloric effect just by looking at magnitude of the pyroelectric coefficient. Okay. So that is the beauty of thermodynamics, it relates seemingly unrelated properties. Okay. So similarly you can also look at what are the piezocaloric effect, right, and you can go back to your potential phi 2 and look at now the mechanothermal properties. So you can look at the piezocaloric effect and show that the piezocaloric effect is the same as coefficient of thermal expansion. What is coefficient of thermal expansion? You apply temperature and then you look at the change in, this is alpha ij, right. You create a strain in the material. What is piezocaloric effect? You apply stress and then you are generating entropy again, right. So these are one and the same, and that is nothing but for lack of a better word, this is also the magic of thermodynamics. Okay. There are other properties like the heat, so heat of deformation, the heat of polarization, etc., right. So these properties are also have their converse properties. The converse property becomes minus f and minus t, right. So I am going to give you in the assignment, so you can actually go home and then prove that converse of f is actually minus f and converse of T is actually minus T, right. So you need to define another potential here. So you can the trick lies in defining a potential of choice, lies in defining an appropriate potential, thermodynamic potential phi I. Okay. So to show that. Okay. So this I am not going to do in class, but I guess you can do it, or if the assignment format permits, we will try to give this in the assignment. Okay. So with that, let me conclude this class by showing you that so various seemingly unrelated properties get related because just by mathematics, the mathematics of these thermodynamic potentials. The curvatures of these thermodynamic potentials are properties, and even the coupled properties can be looked at as some sort of curvature of a thermodynamic so these potential manifolds, right. So in coming from two different directions, and so by virtue of these thermodynamic functions being analytical, so something like converse piezoelectric effect, direct piezoelectric effect are same and equal in magnitude, right. Something like piezocaloric effect and thermal expansion coefficient are same and equal in magnitude. Something like electrocaloric effect and pyroelectric effect are same and equal in magnitude. So my design principle now can be to design a good electrocaloric material. I can just run it through a pyroelectric test, right. So if it is a good pyroelectric material, then the thermodynamics, if you are a believer of thermodynamics, right. So then you would say that it's also a good electrocaloric material, right, and so on and so forth. Okay. So with that we will so next class we will actually look at so the statistical mechanics aspects of this and see so how these what do these properties mean from a very microscopic level, right. So far, okay, so it's some sort of curvature of some manifold, it's a restoring force. So this is the sort of intuition we got from thermodynamics. We look at statistical mechanics and then see how that connects to all these thermodynamic properties that we have seen, so that we understand some sort of a microscopic mechanism of what these properties really mean, right. So from a statistical mechanics perspective. All right. So I will see you again in the next class. Thank you very much.